So what we're doing today is we are going to be looking primarily at series representations for functions, and then we're going to look at the beginning of complex analysis. And when we're looking at functions, you have had whole courses in math on series, and a lot of what you have done is convergence and various other factors of series. What I want to focus on is, in preparation for doing Fourier series and linear vector spaces, is the idea of a series as an expansion and a basis. So we are used to power series, which are often called Taylor series or Maclaurin series, where you do your expansion in powers of x to the n. And we'll review briefly the Taylor series. We will also, in this class, spend a fair amount of time on Fourier series. This is where your expansion is in powers of e to the I 2 pi nx, or cosine nx sine nx. And like I said, we'll be going over that later in the quarter. But it'll have the same basic ideas as what we go over briefly now with power series of x to the n. Then, as you go on in your physics career, you will face all sorts of special function series. For example, there are Bessel functions, which you may or may not, depending what math you've taken, learned about yet. These are j sub n of x. And they can also be things that you can expand a function in. And I think one way to help think about this, right, all three of these are examples of a basis that you use to expand a function. And we're going to go into bases and real details in the linear vector spaces, but I think it's useful to take a step back to what we were doing yesterday and recognize that a basis is the same idea as when we have numbers and we do numbers in different base, like base 10 or base 2. So real quickly, on your piece of paper, if you were going to do it, write 15 expanded out in base 10, and then write 15 expanded out in base 2, where I want you to write it as a coefficient times, for base 10, 10 to some power, or a coefficient times 2 to some power. So go ahead and do that right now real quickly. So 15 in base 10 should be easy. What do we have? Excellent. So what this tells us, since these are our base, what we're expanding in, we have coefficients a sub 1 equals 1 and a sub 0 equals 5. So notice the idea here, and this is the idea behind an expansion. We have some object that has some reality, the number 15. We happen to name it because of our base 10, but the number 15 exists independent of the base I write it in. I then pick a basis, base 10. I then can write it as a sum of coefficients times those basis vectors, in a sense, or in this case, this base. So I have my coefficients and I have my base. So what does this look like in base 2? No.
1 times 2 cubed plus 1 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0.
right? We need to use everything that's powers of 2. And because we're doing base 2, our coefficients can only be 0 or 1. It's binary. So we've got all coefficients of 1 going from n equals 0 to 3. So I have a0 equals a1 equals a2 equals a3 equals 1. Same number, different expansion.
How about we use 1 times 2 to the power of 4 and minus 1 times?
You could do that. That would be a different way of writing it. But the tradition, right, when doing base, is to always use the powers less than what you have and just do addition and no negative coefficients. But that's not relevant really to the main point of the example, which is, as we go forward, keeping in mind that a function is some object that just exists, and there are many different ways to write it. One of the useful ways to write a function is as a series expansion in some base, and we will be looking at a bunch of these in this class. But the two we'll focus on are power series of x to the n and Fourier series. And so now you just need a rule for writing those expansions. And the rule for the Taylor series is what? How do I write a Taylor series expansion for f of x? I take the nth derivative, which I write like that, and I divide by n factorial, and then I multiply by x to the n. And which is basically the Maclaurin series. It's a special Taylor series. Now, the Taylor series, you're right, will more generally have some arbitrary a that I expand about. And when we expand about 0, it gets a special name, the Maclaurin series. But for most of what I want to talk about, we'll be going around 0. This can become x minus a to the n, and this could become fn of a over n factorial, and we still have a sum of n from 0 to infinity. But notice, in both of these, we have our coefficient a sub n, and we have our basis. That's the new way we want to think about these. We want to think about it as a coefficient times a basis vector is the language we'll use. Now, the other little thing is some wording. When we talk about the order, we're really talking about the value of n generally. So we'll have 0th order, 2nd order. And in contrast, we'll talk about the number of terms is literally just the number of terms. So if I look at sine of x, what are the first two terms in the expansion of sine of x about a equals 0? If you're doing a Taylor series of sine of x, your first two terms are, you should know this. Well, it's x.
Oh, sorry.
X
Minus x cubed
over 3.
Yeah.
I'm sorry, 6. Yeah, 3 factorial. Now, notice this expansion is third order, but it has 2 terms. So just be aware of that language, right? If there's a order that is 0, so the 0th order and the 2nd order are 0, we don't really count them when we count the terms. We just count 2 terms. Now, the use of number of terms is not like universally defined by everybody. There might be some people out there in the physics and math world who will call that the 4th term and take into account that you had coefficients of 0. I've never really seen it. I always see it. This is 2 terms, 3rd order. The language of order is pretty consistent. I don't expect any difference there. Any questions on that? Now, there are A few functions you really should have memorized. There's sine, which we already wrote up there. There's cosine of x, which is approximately what for two terms? One minus x squared over 2. There's e to the x, which is approximately what? Which is usually enough, that what you'll need. There's the natural log of 1 plus x. And why am I doing 1 plus x? What's the natural log of 0? Undefined. Natural log of 1 is something you're more likely to expand around because the natural log of 1 is 0. Natural log of 1 plus x is what? Approximately? Anyone remember? That's a hard one. You usually don't memorize it. It's x, and then it's a minus x squared over 2, if I did that right. And then the one I had mentioned in the last class, 1 plus x to the p, and here p could be minus 1. If you remember, we did 1 over 1 minus x. That's the binomial expansion, 1 plus px plus p times p minus 1 over 2, x squared, and so on. And it's this first part that's really the key to know. And the other thing to keep in mind, which I said yesterday, let's just open up a new. Is the Mathematica command that does all of this is series. So if we just take one of these, log of 1 plus x, notice the natural log is the logarithm we use the most in science. So log in Mathematica is the natural log. And we're going to do x. We're going to expand about 0. And we'll go 2 terms just because that's the one I'm not sure I got right. I did get it right. And so you get what Mathematica will tell you, the 2 terms you want, and then it reminds you that the next term is order x cubed. If, let me see if I've remembered my commands correctly. Yes, if you do the / normal, that's because you know you don't want to worry about having that ordered. You're actually going to use that series somewhere, right? If I keep the ordered x cubed, that doesn't help me if I'm then going to use this series in another expansion. But if I do the / normal, then I'm good to go. And it gives me a normal expression. That's how I remember that command. I can also, of course, normal as a function. I can do normal, bracket, series, and the whole thing. Any questions on those basic ideas in series?
What do you mean by normal again?
Normal is just, if you notice what it did to the command, it's the difference. Let's just type them both so you can compare them. It's the output Mathematica gives you. In the one case, it tells you explicitly what your next order is. In the other case, it just gives you the series to the terms you want.